All right, question 9. Recovery of zinc by distillation under vacuum. To get zinc out of lead, you go to distill it under vacuum at 500 C, calculate the vacuum or the pressure, minimum pressure necessary to reduce the zinc content to 1.01% atomic, and you're given, this is the vapor pressure of pure zinc. The vapor pressure of pure zinc, and this is the activity coefficient of zinc in lead. So, okay, so the activity of zinc is equal to the activity coefficient times the mole fraction. The activity coefficient is 11. This is the activity coefficient of zinc that you want to reach. This is the activity of zinc that you want to reach. You want to reach 0.01 10 to the minus 2 mole fraction. So you want to reach an activity of zinc of 10 to the minus 11 times 10 to the minus 4. The activity of zinc, and then is the partial pressure over the solution divided by the equilibrium partial pressure. Okay, so I can take the logarithm of both sides of this. So the log of the vapor pressure of the pure material is that, and you want the activity to be equal to that. So what is the pressure you need to reach? What is the pressure when you have an activity of 11 10 to the minus 4, and this is the partial pressure of the pure material, and so you've got to reach 1.45 times 10 to the minus 3 torr is the minimum pressure that you have to pull on a vacuum in order to get the partial pressure down to that. If you have a higher pressure, then you'll have a higher activity, and hence a higher mole fraction. Okay, so that's your minimum, that's your maximum pressure. You've got to get the pressure below that. This is, of course, assuming that the lead has a negligible vapor pressure relative to zinc, which is a good assumption. Okay, is your process, seeing as how your job is to get the value of the content of zinc down, is this helped or hindered by the fact that you have a positive activity coefficient, or activity coefficient is greater than 1? Ideal solution, this gamma naught would be 1, now it's 11. So does that make your job easier or harder? Easier, okay. Positive activity coefficient greater than 1 means the solution is less stable than an ideal solution, so the zinc is more easily removed. It has a higher vapor pressure. Okay. If we want to look at number 1, go on over here. Okay. Number 1 was the activity of carbon and steel. Okay, so this is kind of a classical method in order to measure the activity coefficient. You would take a boat in a furnace at some temperature T. You pass here a mixture of CO and CO2 in the gas space here. Here you have your iron carbon solution. The gas and the carbon equilibrate so that it's at equilibrium, and then you have CO2 at the exit is assumed to be the value in equilibrium. So you assume that at the exit you're measuring the CO2 that was at equilibrium with the carbon and the steel, so you've got to pass it slowly, of course, and let it reach equilibrium. Then you measure the CO2 ratio outside. So we actually did 2 experiments. If a mixture of CO and CO2, if the CO2 circulates slowly at 1 atmosphere, total pressure above pure graphite, then the CO2 in the gas at the exit is 2.95%, the rest being CO. Then we do the same thing, but instead of pure graphite, we replace it by steel, and we say the steel will be decarburized if the concentration is greater than 6.6%, and will be decarburized otherwise, but I mean that's obviously just saying the same thing as saying that that's the equilibrium percentage. Okay, so you got 2.95% at equilibrium with carbon, and 6.6% if it's at equilibrium with steel. Calculate the activity of carbon in the steel. So that's the equilibrium between the carbon, either pure or in the steel, and the gas. Equilibrium constant. Classical boudoir reaction. The graphite, if in the first experiment you do it with graphite pure that has an activity of 1, So that permits you then to get the equilibrium constant, because in equilibrium with pure graphite, you know that PCO2 is 0.0275, and the partial pressure of CO is 0.9705, the difference from 1. So you know the partial pressures when the activity is 1, so that permits you to get K, and then of course K is the same K even if you don't have an activity of 1. So in the second case you have the same value of K, you have, this is your, okay, the activity of carbon. And if you know the mole fraction of carbon, you can calculate the activity coefficient of carbon. Alright. Number 3. Elimination of copper from gold. To remove copper from gold, you're going to liquid gold. You propose to bubble pure oxygen at 1 atmosphere and 1400. Which oxide of copper is produced, and what is the minimum copper content that you can obtain? And what do you think about this as a practical method? Okay, so first of all, okay, well, what you're going to do is you're going to bubble the, what we're assuming here is you take your liquid, this is your copper gold mixture, and you bubble your oxygen in here, and you're going to form copper oxide solid on the surface, and you're assuming that the gold doesn't oxidize, which it doesn't. So you only form copper oxide in that case. First question, which forms? Well, okay, you have copper oxide, CuO, in equilibrium with oxygen. Which way is this reaction going to go? You calculate delta G. I can calculate delta G0 because I'm talking about pure oxides and oxygen at 1 atmosphere, so it is the standard state reaction. Its delta G naught is positive, so the reaction goes to the left, so copper oxide is your stable oxide. First part. You only get one, not both. If they both form, then this reaction will occur one way or the other to get rid of one of them. Then, okay, so this is the reaction between the copper in the, was it silver or gold, whatever it was, and oxygen CO2O. The Gibbs energy is minus RT log K, so that's your equilibrium constant. The activity of copper oxide is 1 because it's pure solid copper oxide. The PO2 is 1 atmosphere, and this then allows you to calculate the activity of copper at equilibrium, which is gamma times X, so X is 0.22. So that's the minimum. You can continue to bubble the oxygen forever. You will never get the copper content below that. Obviously a pretty crummy method if you want to get copper out of here. These are really simple, don't about that. Number 4, recuperation of silver from a lead bath. Okay, when you make lead, lead ore contains silver with it. Lead sulfide contains silver sulfide. So when you make lead liquid, when you make lead in a carbothermic pyrometallurgical process, you end up with quite a bit of contamination with silver because it gets reduced too. To get the silver out of lead is a problem because it is less reactive than the lead. You can normally, a standard method in metallurgy to remove more reactive metals is to say bubble oxygen through it. If you have silicon and steel, you bubble oxygen, and since silicon oxide is more stable than iron oxide, you preferentially oxidize the silicon. Okay, so you can always remove a more reactive element by reacting it with some gas, but you can't remove a less reactive element. That's why copper is such a problem in steel, in steel scrap, because you can't get it out by bubbling oxygen through it, because the copper is less reactive than iron. Okay, so when you're making steel scrap, you try not to put in any generators or electric motors that might have copper turnings in them when you're crushing the car. Anyway, so getting silver out of lead is the same problem. However, there is a trick they use. This is just by chance. There is a solid intermetallic compound. This is not a general, called Ag2ZN3, which is a very strong, has a good strong Gibbs energy of formation. And what happens is if you add zinc to your silver, you will form this zinc, that is Ag2ZN3 intermetallic, and it'll float to the surface and you'll get rid of most of your silver that way. Okay. So, and you have the equilibrium constants here, and this you got the Gibbs energy. So what is the silver content after this process has been completed. Okay. Also then it depends on how much zinc you add. That after removing the silver, the zinc content will be 0.0146. You add enough zinc to do that. So now you get then, so that's the reaction. The delta G naught is minus RT log K, and there's your K. Okay, so your activity of the complex is 1 because it's pure. The activity of silver is the activity coefficient times the mole fraction. The activity of zinc is the activity coefficient times the mole fraction, which was a given in the thing, and so you reduce the silver to 10 to the minus 4. And then you end up with this much zinc contamination. If you add more zinc, then you will end up with more zinc dissolved at the end, and you bring down the molar fraction of silver, but you increase the contamination with zinc. So you're replacing the silver by zinc. Okay, so this is what you're going. So you're bringing the silver down to 10 to the minus 4, and now you've got 1% zinc in there. You can add more zinc and to get this lower, so you try to figure out what you need and then add the minimum amount of zinc necessary to get it down to that. Okay, so now you've got a contamination of zinc that was bigger than your contamination of silver to start with. First of all, the silver is merely contamination. The reason you want to remove it is you want to sell it. You don't want to sell it with your lead. You like to get it out and sell it separately. It doesn't really harm lead too much to have a little silver in it, but you can actually make more money by selling the silver that's in the lead than you can by selling the lead. So that's why they want to get the silver out. But anyway, now you've replaced it by the silver by zinc, but now that's not a problem because zinc is more reactive than lead, so you can react the zinc can be reacted with chlorine. So this is, you can react the zinc. Now you can bubble chlorine through it, and that'll preferentially chlorinate the zinc because zinc is more reactive than lead. So you've replaced a less reactive element silver with a more reactive element zinc, which you can then remove by the classical method. You don't use oxygen, you use chlorine for various reasons, but then you form zinc chloride and get rid of it. Okay. Then what did I say? Number 6. Okay, this is composition of an oxide coating layer on cobalt nickel. So you have a cobalt nickel alloy oxidized at 1650. The oxide layer is a solid solution of COO and NiO, which form a solid solution. At the interface they're in equilibrium. The composition of the alloy is X copper is 0.51. What is the composition of the oxide? Okay, so this is a very classic gas, or you say metal oxide or metal nonmetal or metal slag or whatever equilibrium. This is, you have an exchange reaction. We have two layers here. You have here you have a metal, which is a cobalt nickel solution, and up here you have an oxide, which is a cobalt oxide nickel oxide solution. Okay, and they're in equilibrium at the interface. So we assume that at this interface here, there's an equilibrium formed between the two phases. There's an oxygen gas out here. Neither phase they're not at equilibrium with the oxygen gas. The oxygen gas is oxidizing the this into a container of some sort, so the oxygen gas comes in this way through the pores or something. Okay. But so this is forming. So this is actually, here you have two solids, but I mean this would be the same thing as if this was a liquid metal and that's a slag. Okay, it's an oxide, a metal phase and a nonmetallic phase containing the same elements. And you're assuming they're not at equilibrium with oxygen. If this goes on, the alloy continues to oxidize, but that's relatively slow compared to, say, the fact that at the interface we're assuming we have an equilibrium at the interface. Okay, it's the same as bubbling oxygen. You could have iron silicon, and this could be iron silicon, and this is FeOSiO2 liquid slag, and you're assuming that you're oxidizing the silicon, trying to get it up into the slag. Okay, so this is your exchange reaction between cobalt and nickel in one phase and nickel oxide and cobalt oxide in the other phase. So you always write the exchange reaction, which is the difference of the two oxidation reactions. Okay, so that gives you RT log K, which is the ratio of the activities. in one phase to the ratio of the activities in the other phase. Okay, so clearly if this reaction is delta G0 is very negative, you have a large K which favors nickel in one phase and cobalt. Okay, if this was very negative, it would favor nickel in the metal phase and cobalt oxide in the oxide phase. If it was positive, it would go the other way. Okay, it's actually reasonably close to 0. The K is just slightly greater than 1, so it goes slightly to the left. But at equilibrium, you're going to have a reasonable amount of cobalt and nickel in both phases. So at equilibrium, or we said that the metal phase, we're assuming an ideal solution, so the activities are equal to the mole fractions. This is the ratio of the mole fractions, or hence the activities in the metal phase. Okay, so this is the ratio of the mole fractions in the oxide phase, the mole fraction of nickel being 1 minus the mole fraction of cobalt oxide. And if you solve this, you get 0.85, which means that because sorry, the K was negative. Sorry, the delta G was negative, so the K is slightly greater than 1. So the reaction is displaced somewhat to the right. So at equilibrium, your nickel, you have about a 50-50 here, and then the cobalt goes more into the oxide phase than into the metal phase. So even though your metal is 50% cobalt, your oxide is 85% cobalt. If this delta G were more negative, then you would even have more cobalt. Okay, but now, unlike the previous example, say the example with the copper gold alloy, you only got copper oxide because the gold was not, gold oxide was not stable. Or even if you have two oxides that are immiscible, then you'll get one or the other. If cobalt and nickel oxide were immiscible, didn't form a solution, then you would get either cobalt oxide or nickel oxide, because this reaction would go either you'd have, the activities would be one on one side. Both activities would be 1, so the reaction goes one way or the other. Since the activities are not equal to 1, because it's a solution, you will always get a mixture. If this is very, very negative, you would get mainly cobalt oxide, but you'll always have some nickel losses in the nickel and the oxides.
You have written down the exchange reaction. What if I write the equation for each sub-reaction? I get slightly different.
If you do that, you'll find that both of them are negative. So, no, you'd have to then assume that the equilibrium pressure of oxygen, you can't use 1 atmosphere, you can't use the 1 atmosphere oxygen, is that what you did?
Yeah, but if I divide the two equations,
you should get exactly the same result. So the oxygen cancels out?
Yeah. Because
you took the 2 Ks, divided them,
yes.
You should get the same answer.
It should be okay.
It should be the same. It could be just a numerical error. If I understand you right. You write one equilibrium constant with PO2, you write the other, you divide them, you subtract, cross out the PO2s, you get the same answer. Number 7 is exactly the same thing, really. I mean, same thing, you electrolyze aluminum. Aluminum is made by electrolyzing cryolite, Na3LF6. And so Na3LF6 can be a liquid, is really a mixture of sodium fluoride and aluminum fluoride in the liquid state. And the activity of aluminum fluoride and cryolite is 0.414, and of aluminum fluoride is this. Okay, so Na3ALF6 is more or less the stoichiometry, but the cryolite is a liquid, a mixture of sodium fluoride and aluminum fluoride at about a 3-to-1 ratio with these activities, which are known. You can find that in the literature. And it's made so you electrolyze the stuff and you get aluminum, but now you get an exchange reaction too. Since there's sodium fluoride in the bath, in the molten salt, you're going to get sodium contamination in your aluminum. There's no way around it. Calculate the composition of sodium at the when it's created in the Hall process. So this is again your exchange reaction. You have your two phases. It's exactly the same as this. You have in your bath, you have 2 phases. Here you have aluminum with some sodium, and up here you have your cryolite, which is a liquid mixture of sodium fluoride and aluminum fluoride. Even though it's pretty much 3-to-1, it's still one single liquid with an activity of each of NAF and ALF3. And so you write the same thing. There's the exchange reaction. Same thing, the fluoride's in one phase and the metal in the other phase. you do the same thing, and you get the equilibrium constant. Now the equilibrium constant is very large. This is a very negative reaction. That is, sodium fluoride is much more stable than aluminum fluoride, so this reaction is displayed strongly to the right. So you've got a very large equilibrium constant, which mainly favors sodium fluoride and aluminum rather than sodium aluminum fluoride, but there's still going to be, it's not infinite, so there's still some sodium. So the activity of aluminum is pretty close to 1, because, I mean, you're going to have very small amount of sodium. The activity of sodium fluoride and aluminum fluoride are given, and now here you have the activity of sodium, which is the equilibrium constant, sorry, the activity coefficient times the mole fraction at equilibrium. So at equilibrium you can solve for the mole fraction of sodium, and you get 58 parts per million of sodium as the equilibrium content of sodium made by the Hall process at that temperature, roughly. You see you have a very positive, a very large gamma Henry, a very large activity coefficient. Okay, that is, the sodium is not particularly stable in the molten aluminum, and that helps you. This being larger means the X-sodium is smaller at equilibrium. So the sodium doesn't really want to go into the sodium aluminum. If it did, then we'd have big trouble. Okay, if sodium and aluminum were an ideal solution, you'd have way more sodium at equilibrium than you do. Even this is too much to make. You can use this for some applications, casting that, but if you want to make you want to roll out a thin sheet for a beer can, then the sodium causes hot shorting, you get cracking. This has to be removed later on, usually with chlorine. The sodium, again, being more reactive than aluminum. But it's exactly the same principle as the cobalt, nickel, and any of these things. It's always you write the exchange reaction. Okay, so then just to prove a point, number 8 was again the same thing. This is sulfuration of nickel, so it's the same thing as here, except here we had cobalt nickel, now we have copper nickel. And now the difference though is here you have nickel sulfide and copper sulfide, but they are not miscible. They form two different phases. Okay, it's either one or the other. And now you don't get both, you get one or the other. Okay. The sulfides are solid and immiscible at this temperature. So you get, you write the exchange reaction, but now these two activities of nickel sulfide and copper sulfide are both equal to 1. Okay, so now the question is simply, is the equilibrium constant will give you the equilibrium ratio of activity of nickel to the activity of copper. Okay, the Q, which is the actual, or Q is the actual ratio, so these are the actual activities, okay, which is less than K, so the reaction is going to go to the right. Okay, these are the, K is the actual ratio at equilibrium. K is the equilibrium ratio. Q is the actual ratio. These are the actual activities at equilibrium, in the actual alloy. And these would be both active. If they were both there, the activities of each would be 1. This is less than K, so the reaction goes to the right, and you only get copper sulfide. You don't get any nickel sulfide.
What's the difference between the question 8 and 3? Because we usually consider delta G, which is equal to delta G naught plus RTL.
3 is. Yeah, well, you could write it. This is just one way of doing it. You compare the equilibrium constant to the actual ratio. The other way I could do it is I could calculate delta G is delta G naught plus RT log of the actual ratio, and I would find out that delta G was negative.
Yeah, but what about the question 3? Because in question 3, the delta G of reaction is equal to delta G naught.
Well, yeah, but that's only because the oxygen pressure is 1 atmosphere. So. In question 3, delta G is, yeah, delta G is delta G naught because you have pure copper, the pure copper oxides and the oxygen's 1 atmosphere, which is the equilibrium oxygen pressure. I mean the standard state oxygen pressure. 11 was. Yeah, this is a way, I don't know, this is a way of measuring, if you see this, Okay, the activity, if you want to measure the vapor pressure, you can measure, one way of measuring activity is by measuring the vapor pressure. So the activity of a component is its vapor pressure over the solution divided by the vapor pressure over the pure material. Okay, so there's different ways of measuring vapor pressure. You can measure it directly. I mean, if you have, here you have your material, and here you have a pressure gauge, a little manometer, and you can measure the pressure, but obviously only if the pressure is reasonably high. Okay. You can use a mass spectrometer. You know, mass spectrometer work, we'll talk about that later, but the mass spectrometer gives you a very low, that's only good for very low partial pressures. The medium range of partial pressures, one method that is used classically is called the transportation method or the transport method. And what you do is you say, well, here's the example of the transport method. We try to find the activity of cadmium in the cadmium-lead solution, so we pass argon very slowly. And we assume that the argon becomes saturated. In other words, an equilibrium vapor pressure is established up here above the melt. So we assume that the melt here is in equilibrium with the vapor phase above it. So the partial pressure in the vapor phase is equal to the partial pressure, the vapor pressure of cadmium. The partial pressure of cadmium is equal to the vapor pressure. The vapor has become saturated. Then you pass the argon very, very slowly, and you assume that the argon is passed so slowly that the vapor pressure up here still remains constant. In other words, the argon removes the cadmium, but the cadmium replaces the argon, replaces the cadmium that was removed. Okay, so then you can measure you pass a certain volume of argon, and you condense the cadmium here, and you can work out how much cadmium that argon contained, and that will then give you the vapor pressure. You've got to pass it very slowly. If you pass it too fast, you sweep away the cadmium faster than the liquid could replenish the gas phase, and you're going to get a partial pressure which is lower. So what you do is you do this at various flow rates, and you plot it until you reach a plateau. Then you know you're going slow enough. And of course, if the lead is a vapor pressure, you're going to get lead down here too, but that's okay, because then you can actually analyze this, and you get the cadmium and the lead, and you get the two vapor pressures. Okay, so that's called the transport method. And that's good for partial pressures in sort of the range 10 to the minus 4 atmospheres, 10 to the minus 7 atmospheres. Higher than that it doesn't work, lower than that it doesn't work either, so it's kind of an intermediate range. Used to be used more in the past, but people still use it. So the number of moles of cadmium that condensed, we said that during the certain amount of time you had 11.24 grams of cadmium condensed, which just happens to be 10 times the molecular weight of cadmium. So 0.1 moles of cadmium were formed in the condensate. During that time, this is the volume of argon that passed. 6,400 liters passed during the 6.4 times 10 to the minus 3 whatever hours. Okay, so 6,400 liters of argon contain 0.1 moles of cadmium. Okay, so the number of moles of argon was PV over RT. So you had 111.5 moles of argon, which contained 0.1 moles of cadmium, assumed to be at equilibrium with the liquid. So the partial pressure of cadmium is the mole fraction of cadmium in the gas times the total pressure by Dalton's law. Okay, so the partial pressure of cadmium is this. Okay, under the assumption that the gas was saturated with the cadmium. The partial pressure of pure cadmium is given in the, but you could measure that. You could just repeat the experiment with pure cadmium and measure the partial pressure of pure cadmium. So the activity of cadmium is 0.272. That's a classic method, a classic transport method of measuring the If it does require you to make the assumption that the cadmium is monatomic gas, because if the cadmium was diatomic, then you would have to put pressure of cadmium 2 over P naught cadmium 2 to for partial pressures below about 10 to the minus 9 or so, they use the mass spec technique. everybody know how the mass spec technique works? You take a cell here called a Knudsen cell. Oops. I'm getting into an Escher thing here. Not supposed to be. Escher ever drew a Knudsen cell. So here you put your material. This is your AB liquid or whatever. And here you have a very small hole whose dimensions, length and diameter are known very, very accurately. Up here you have the gas. And if the gas, so in the gas you will have various molecules. You'll have A, A2, whatever. You'll have B, you'll have B2, you'll have AB, you'll have A2B. These are gaseous molecules in the gas phase, all at equilibrium. They're all in the vapor pressure equilibrium. And they're at very low pressure, so the pressure is, say, less than 10 to the minus 9, something like that. So the gas is very dilute, so a gas molecule, from time to time, a gas molecule will go out through the hole. And if the gas pressure is very low, there is an equation which relates the diameter of this and everything to a simple equation to the gas partial pressure of that molecule. If the gas pressure is too high, then you get collisions and everything. You can't really work it out, the number of molecules escaping per second as a function of the partial pressure. So the length of this thing has to be fairly short compared to the mean free path between gas collisions in order for the thing to work. That's why it really only works for low. Okay, then what you do is up here, then you have a mass, this thing goes through, then you ionize, goes through a mass spectrometer, which ionizes the gas. So the different molecules have different ionizations, different charges on them, different weights, and so then here you have a magnet, then the gas splits up. You then have the charged molecules, which are they're charged, and then they go through a magnetic field, and since they have different masses, they get separated. So the mass spectrometer separates them, and then up here you can put a counter. You move your counter around, and you can get how many molecules per second of each of the different molecules is. Okay, so you separate the gas and you can get the number of molecules per second of each different kind of gas, and from the angle that they were scattered, that they were bent because of the magnetic field, you can work out their mass, so you figure out what they are. So what you end up with is you end up with the partial pressure of every single molecule, which is exactly what you want. If you want, you can calculate so then you can calculate the activities of A and B, because you know how much there is of everything in there. Okay, so you need the mass, this is called a Knudsen cell. Knudsen cell, so you have the Knudsen cell combined with a mass spectrometer, and it's a very powerful technique for analyzing the gas phase. But it only really works if you have quite low partial pressures. But this is really good for, say, metallic phases, liquid metals, tungsten, tantalum mixtures or something where the partial pressure really is 10 to the minus 11 and so on. Yeah.
Why the orifice length is to be lesser than the mean free path of the gas, just to avoid collision?
Yeah, apparently if you have, I won't pretend to be an expert in the theory, but if you have too many collisions among the molecules and of themselves and with the walls of the hole and everything, then the equations that relate the number of molecules leaving to the partial pressure becomes basically insoluble. It depends too much on. This really requires it. It isn't. So in the equations, some of the collisions are taken into account, but you're assuming there are not too many, that they're pretty much independent. Otherwise, I understand you just can't really resolve the thing. Okay, so really, if you want to measure the partial pressures, you at high pressure you measure directly. At lower, 10 to the minus 3 and 10 to the minus 7, you can use the transport method. Below about 10 to the minus 9 or something, the Knudsen cell is. Okay, the Knudsen cell then obviates the necessity of the, you don't have to assume it's monatomic, diatomic, you find out what it is. You do a good measure. And you measure all the activities simultaneously. Which you could still do in this transport method here. If you did have some lead, this was a cadmium lead mixture, if you did have some lead condensing, you could weigh. You'd have to separate it out in the condensate, but then you would also get the lead activity. Okay, let's go on to number So number 7, chapter 7 was the Gibbs-Helmholtz equation. Well, this is straightforward for the oxidation. For this following reaction, which is the oxidation of manganese, this is the standard Gibbs energy. Delta G0 is a function of T, measured somehow. Okay, measured, probably equilibrating the metal and the oxide with gas phase and so on. Anyway, delta G has been measured by measuring basically the part. If you measure the partial pressure, the delta G0 is minus RT log K, so if you put your manganese in equilibrium with manganese oxide, measure the equilibrium oxide. Calculate the heat, the enthalpy. Okay, so you use the Gibbs-Helmholtz equation. This is the best form to do it in. dG naught over T, D1 over T is delta H. So take G naught over T, differentiate it with respect to 1 over T, and you get an expression for delta H. And at 800 degrees, that's what it is. Number 5. Nickel and nickel. Okay, the ratio of pH2S, pH2 at equilibrium with solid nickel and solid nickel sulfide has been measured at several temperatures. So this is again the classic gas equilibration technique. I showed that in the question 6. Question 6.1 for the iron carbon thing. It's the same thing. Now you have a boat here containing what again is it? Nickel. And nickel sulfide contains nickel and Ni3S2, a mixture of the two powders. So it's powder, so you have a large surface area. Here you pass mixture of H2 and H2S, and you assume that it reaches, there's an equilibrium. The gas passes very slowly, and you reach this equilibrium then is reached between the gas phase and the solid phases, and then you measure the H2 and H2S pressures at the exit, and you assume that's the equilibrium pressure. Okay, so you measure that, and then for this reaction then delta G0. So this is your equilibrium pressures at various temperatures. So it says calculate delta G0 of the following reaction, and calculate the average values of delta H and delta S over that temperature range. And it asks you also for delta Cp, the change in Cp of the reaction, is it positive or negative. So what is that? Number 5. Remember I'm at 5. Okay, so that's the reaction. The equilibrium constant is the ratio of the partial pressures at equilibrium, which you measure, and then delta G naught is given by that. So delta G naught, then I've calculated delta G naught from the data at different temperatures. And if you plot delta G naught as a function of T, you will get almost a straight line. Okay, so delta G naught is delta H naught minus 2 delta S naught. Supposing that it is a straight line, I drew the straight line by hand through this particular graph myself, and I got delta G naught. This was the equation of the line. You can do it by least squares or whatever you want, or you can actually fit the thing up to whatever you want to do. I just draw the straight line. So then delta G naught, this is the equation of this line that I drew. So therefore delta H naught is minus 46,000 and delta S naught. That will be the average value. Assuming it's a straight line, I've got the average value. In actual fact, the line isn't exactly a straight line. In other words, the slope of the line is, if it is a straight line, the slope is minus delta S naught, average of course. If it is not a straight line, the slope at any temperature is minus delta S naught at that temperature, because that's the Gibbs-Helmholtz equation. d delta G dt is minus delta S. Okay, so the line actually bends slightly this way if you drew it. Okay, and so at any temperature, if you drew the tangent at that temperature and extrapolated it to 0 Kelvin, that is the heat of the reaction, that is the enthalpy of the reaction at that temperature there, and the slope of the line is minus the entropy of the reaction at that temperature. Okay. So the Gibbs, if it's a straight line and you extrapolate it to 0 Kelvin, the intercept is obviously delta H, because that's the straight line. If it's not a straight line, but you draw the tangent at a given temperature and extrapolate the tangent to 0 Kelvin, the intercept is the enthalpy at that temperature. So now clearly then, as I increase the temperature, the tangent, the intercept here moves up. Okay, as I increase the temperature, the tangent goes around this way, so the intercept increases, so d delta h dt is positive. But d delta h dt is the delta Cp, so delta Cp is positive. Now, if the data were extremely accurate, then of course you could get not just the sign of delta Cp, you could actually get delta Cp from the second derivative. But I don't think you were ever going to get anything that accurate. So, I mean, this gas equilibration method, what you're measuring is delta G. So delta G0 is quite accurate. Delta H and delta S, which are obtained by the temperature dependence, are the derivatives, so they're going to be less accurate. Delta Cp, which is the second derivative, is going to be even less accurate. So measuring delta H and delta S by the Gibbs-Helmholtz technique is great, but it's not the primary thing you're measuring, it's a derivative, so it's going to be less accurate. And there was number 3 on the Gibbs-Helmholtz equation again. Number 3 was the vapor pressure of water is given at 2 different temperatures. Calculate the vapor pressure of water at another temperature. Okay. So you've got to obviously extrapolate the vapor pressures. You got 25 and 50, so you're going to extrapolate the vapor pressure from, you have 2 values of 25 and 50, you're going to extrapolate the vapor pressure to 75. But what equation are you going to use? Are you going to extrapolate the vapor pressure as T or as 1 over T or log vapor pressure? If you want to extrapolate, you want something that's pretty close to a straight line. So that's where you use the Gibbs-Helmholtz equation to decide how you're going to do the extrapolation. If you just plot P versus T, it ain't going to work because it's not a straight line. So this is your equation. This is your equilibrium. You have an equilibrium between liquid water and gaseous water. And the delta G of any reaction is minus RT log K. Okay, so this here is delta G is minus RT log K. K for the reaction is the equilibrium vapor pressure divided by the activity of the liquid. Just like any chemical reaction. There's no difference here. Delta G0 is minus RT log of the equilibrium constant, which is the partial pressure of the gas divided by the activity of the liquid. The activity of the liquid is 1 because it's pure water. So the partial pressure of the gas at equilibrium, which is the vapor pressure by definition, is equal to delta G0. Okay, so if I plot RT log of vapor pressure versus 1 over is equal to delta H minus T delta S. Okay, so if I plot RT, I could plot RT log P versus temperature. The slope would be minus delta S, the intercept would be minus delta H, like in the last question. Or I can do it differently. I divide through by RT. I'm just dividing through by it. It's the same thing, and I plot ln vapor pressure versus delta H versus 1 over T, and now the slope is minus delta H and the intercept is delta S. It's the same. Or this is just the Gibbs-Helmholtz equation, d delta G over T, d1 over T is delta H, whatever. Okay, so if I plot log vapor pressure versus 1 over T, I'm going to get something that's pretty close to a straight line, because delta S and delta H of vaporization are more or less temperature independent. Of course, it isn't a straight line because delta S and delta H depend on the temperature, but over 25 degrees, the heat of vaporization and the entropy of vaporization don't vary that much. The difference, of course, is the integral of Cp, delta Cp over T, which is not 0 by any means. This is not maybe the greatest approximation, but if you only had 2 points, then this is the only way you would do it. And since you're only going 25 degrees, it's probably not too bad. So assuming the heat of vaporization is not a function of T, so if I just take the 2 points here, I can extrapolate them up to 75. I could just draw a straight line between these 2 points and extrapolate it to 75 degrees. Well, I did a graphical solution. Or you could get the heat. You could actually get this equation if you want and extrapolate it analytically, however you want to do it. But the point is, if you're going to plot vapor pressure versus, you have vapor pressure of 2 temperatures, you want to do the 3rd temperature, you got to find an equation that gives you roughly a straight line, and so you use the Gibbs-Helmholtz equation. So that's why if you plot log vapor pressure versus 1 over T, it's roughly a straight line because of the Gibbs-Helmholtz relation. Okay, let's go on to, of course, in all these, series 6, 7, 8, 9, 10, 11, you're welcome to do the other questions too if you want. If you're having problems, you want to try some of the other numbers that are in number 6, number Series 6, number 12, if you want to do try, most of them, the answer, the numerical answer is given, as you know. If it isn't, or you can't figure it out, if you want to do one, I'll be happy if you want to. If you have any questions and you want to see me in my office or something, I'll be happy to show you how to do it. Don't hesitate. So now we were going to do Series 11. Series, where am I? What series am I in? Okay. Where'd this come from? Okay. The tree sounded good. How about that? Okay, number 11 is on solution properties, partial properties, and so on. So number 1, this is to play with partial properties, heats and mixing activities. Cadmium antimony mixture, this is liquid cadmium antimony at 773. The Gibbs energy of mixing and the heat of mixing are given here. So this is the integral Gibbs energy of mixing, and this is the integral heat of mixing as a function. They're completely miscible. So that's the Gibbs energy of mixing, and that's the heat of mixing. And you can suppose that the heat of mixing and the excess entropy are temperature independent, which is usually is what's done in these high temperature solutions. In other words, delta Cp of mixing is fairly small. And you're asked to calculate these various functions. So, different ways of doing it. Okay, so you're given the Gibbs energy of mixing at 773. So first thing was to calculate the excess Gibbs energy at 773. The difference between the integral property and the excess property is the ideal property. The ideal mixing is minus RT x1 log x1. So this is delta G excess is the actual minus the ideal, and that is the ideal expression for the ideal Gibbs energy of mixing of a solution, x1 log x1 plus x2 log x2. I can calculate the excess entropy then as the difference between the heat of mixing and the excess Gibbs energy. Okay, because the excess Gibbs energy is equal to the excess enthalpy minus the ESX entropy, but that is the same thing as the heat of mixing because the ideal heat is 0. Okay, so the temperature is 773. So at 773, which is the temperature of measurement, I can calculate the excess entropy. So now I have the heat of mixing and I have the excess entropy, which I'm assuming are temperature independent. So now I can use the equation Gxs is delta H minus Tsxs to calculate Gxs at any other temperature. The measurements were at 773. I measured G and H, so I get S. If I assume that S is independent of temperature, then H is... By the way, you might prove that if H is independent of temperature, then S, for any reaction, delta G is delta H minus T del. It's from the Gibbs-Helmholtz equation. If delta H is temperature independent, then delta S must be. And if delta S is temperature independent, delta H must be. Either they're both depend on temperature, or neither depends on temperature. You can't have one or the other. Good exercise to do with the Gibbs-Helmholtz equation. Okay, so these are the equations I used to get the excess Gibbs energy at 773, the excess entropy, and the Gxs at 1100, and those are that I plotted. I drew a table here. I just put those values in the table. Then to get the excess partial properties, I calculated them graphically. Okay, this was Gxs. Here, this was Gxs at 773 is that curve here. And if you want to calculate the partial Gxs partials at a given composition, you draw the tangent to the curve. If you want to calculate the Gxs, the partial Gibbs energies partial excess Gibbs energies at whatever composition. You draw the tangent to that curve and extrapolate it to the axes. So here we plotted GXS. That's the GXS with the points that were calculated, and at a given composition, whatever composition here, x prime, you draw the tangent to the curve, and this point here is GXS of whatever this was at that side, antimony. This is GXS of antimony, and this point here is GXS of cadmium at that composition. Okay, so if you do this at different compositions, rotating it around, and clearly then what you're going to get is then this was the GXS. I used the curve at 773, so the GXS, the integral GXS goes from obviously 0 to 0. The GXS of cadmium over here goes from 0 here, the intercept, and then it continues up. The GXS of antimony is the other intercept. Incidentally, they all three meet at the maximum point. Clearly at the maximum point you have a horizontal tangent. Okay. At the maximum the tangent's horizontal, so the two intercepts and the integral property are the same. Okay, so the three lines meet at the maximum. And it's worth noting that these go up to limiting values. They do not go up to infinity or minus infinity. I didn't draw this on the graph, but this goes up and it would meet at 2300. It would meet the line at 2300. So that is the excess Gibbs energy of cadmium in pure zinc. It's not equal to infinity. If this was not the excess property, but you were actually plotting the integral property, if you plotted delta, rather than GXS, if I plotted, and that, well, okay, that's related to the fact that the limiting slope here, that the tangent, the limiting tangent at 0 does not have an infinite slope, it's a finite slope. If you were to plot delta G, rather than GXS, but delta G, then the curve would come down with an infinite slope, so the intercept at 0 would be infinity. This is because of the delta G ideal term, which is r log x, and d log x is, or log x is equal to minus infinity when x is 0. The GXS term, however, is not. Which is the basis of Henry's law, which we'll come to in a little bit, but Henry's law basically says that. The GXS, why is the integral, why, if this is pure cadmium, why is the GXS of zinc in pure cadmium equal to minus infinity? It's because of the r log x term. Okay, the entropy of mixing, the excess entropy of mixing of zinc is minus r log x. Okay, when x goes to 0, log x is minus infinity. But what does that mean physically? It simply means that, well, the log x is based on the distribution, and basically the number, well, you're not, the number of ways when you have a very large, putting the first atom in, if you have a extremely large amount of a material, the number of ways of adding one atom of zinc is equal to infinity. Okay, but the excess Gibbs property is due to the fact that you don't actually have an ideal solution. It's due to the difference in bond energy. If it's an ideal solution, it means that putting an atom of antimony into the pure cadmium, the bonds have the same energy. Okay, so it's an ideal solution. But the excess is due to the fact that the bonds don't quite have the same energy, so that when I put this atom of antimony into the cadmium, it forms this energy which is a little bit different. But it's not an infinite energy, it's the excess entropy, it's the excess energy. Okay, so if I put in the, as I'm adding antimony to cadmium, the ideal entropy term, the entropy term at the limit is minus infinity because there's an infinite number of ways of putting it in. The excess term is due to the fact that the antimony-cadmium bonds have a different energy than an antimony-antimony bond. Okay, and that gives you the excess partial property, but which is obviously not infinity, it's just the difference. We'll come back. All right, so that gives you the excess partial GXS. So I find the excess partial properties graphically. The excess partial property is by definition RT log gamma, or that's the definition of gamma. So the excess GXS of cadmium is RT log gamma cadmium. Okay, so that would permit you to calculate gamma cadmium from this equation. You got GXS here from your tangent intercept. Use this equation to calculate gamma cadmium, and then the activity is the mole fraction times gamma. So That gives me the activity of cadmium. And there's GXS at okay. So when I plotted this out, the activity of cadmium looks like we'll do that. Activity of cadmium looks like that. Okay, so this was the activity goes from 0 to 1. This would be the ideal line. The activity of cadmium equals mole fraction. The GXS is negative, so the solution is slightly more stable than an ideal solution. So the activity is always slightly less than the activity in an ideal solution. Lower activity means more stable. It's less likely to leave. It wants to stay in and has a lower vapor pressure, whatever. Okay, so the activity gets lower. And you always have this typical shape that this is pure cadmium over here. And the activity of cadmium goes to 1. Obviously for pure cadmium, by definition, the activity of cadmium is 1. Okay. But it goes in asymptotically along the ideal line. You often see that Raoult's law says that the activity of cadmium is equal to 1 in pure cadmium. That's wrong. No, the definition is the activity of cadmium is equal to 1 in the standard state. Raoult's law says that this comes in asymptotically to the ideal line, that the slope is equal to the ideal slope. Okay, it doesn't come in. It would have to go through here by definition, but it doesn't come in this way. It comes in. So the activity dx is equal to 1 in the limit. Okay, that it comes in asymptotically. That's Raoult's law. Henry's law says that this slope down here, that the slope here is neither 0 nor infinity, that it comes in with a finite slope at the limit. You also see Henry's law written saying that, well, you can assume, so what this means is that the Henry's law simply says that the activity coefficient is not infinite or 0 down here. So the activity coefficient of cadmium, so as x cadmium approaches 0, the activity coefficient of cadmium equals gamma naught cadmium, x cadmium, and gamma naught cadmium is not equal to 0, and it's not equal to infinity. It has a finite value. That's Henry's law, basically, although you hardly see it. And you'll see then it says, they say, well, you often see Henry's law saying, well, the activity coefficient of cadmium in the limiting case is a constant. It's not a constant, but since it's not infinite, there's always a region here where you can more or less assume that that's a straight line. That's all you're saying. So you're saying that if you know the limiting value, the gamma naught, if you take the limiting slope, if I took the slope here, if I took the slope of this line at the limit, at pure antimony, and I made the tangent over here, then the intercept here would be the limiting activity coefficient. Okay, so I mean, I'll just take the slope to this line at this endpoint, extrapolate the tangent out here, then obviously this intercept is gamma naught cadmium and when x cadmium is 0. I think this is what. So I'm going to take this is this graph here, the activity, this is the activity of cadmium, this is pure cadmium here. I take the limiting slope here, take the slope at 0 and I step it up here. And this is called gamma Henry. Gamma is 0, doesn't mean ideal state, it doesn't mean standard state, it means limiting case. This is called the Henry activity coefficient, or gamma Henry. It's gamma Henry cadmium is simply the limit as x cadmium approaches 0 of gamma cadmium equals gamma Henry cadmium, and it's not 0, it's not infinity, it's a finite value. That's Henry's law. Okay, and Henry's law. Now, it doesn't mean that the black line here is not a straight line, but clearly there's a certain region of composition where it's a reasonable assumption to simply replace the black line by this blue tangent, so that there's a region of composition near x cadmium is 0 where you can reasonably assume that x gamma naught cadmium is roughly constant, although it's always, of course, changing. And that's just based on the fact, there's nothing more complex to that than the fact that the limiting slope here is more or less a straight line over a small region. Or what does it mean physically? Why is gamma not equal to 1 as an ideal solution? Well, it's because if I take a large bath of cadmium and I put in an atom of antimony, it finds itself in a different environment than in pure antimony. It's surrounded by cadmium atoms, so there's an energetic contribution. If I put the second atom of cadmium of antimony into the cadmium, it's going to find itself again surrounded totally by cadmium, because the probability that those two antimony atoms are going to be next to each other is extremely small. Okay, so as I continue to add antimony to the cadmium, each antimony goes into the same environment as the previous antimony, that is completely surrounded by cadmium. So in that case, you've got more or less a straight line. But as the composition gets higher and higher of antimony, of cadmium rather, as less and less, more and more antimony, you eventually get the point where, no, this is cadmium, more and more cadmium in the antimony. I'm saying it backwards. This is antimony, we're putting cadmium in. The first cadmium atom, the second cadmium atom, the third cadmium atom in the big bath of antimony go into an environment completely surrounded by the solvent antimony. But as you get more and more cadmium, eventually the cadmium ions start to get next to each other. And so then each additional cadmium atom is seeing a different environment from the previous one, and so you start to get a curve off the linear. But that's basically Henry's law. When you say gamma naught cadmium is approximately constant, that's what you're saying. As you put a very dilute solution, the probability that the solute atoms, cadmium, see each other is very small, so each additional cadmium atom goes into exactly the same environment as the previous one, so you get a straight line. Okay. There's activity. I did plot the excess entropy, and you can see here the excess entropy, this funny shape. I doubt if that's at all real. But this just shows you the, again, the excess entropy is a derived quantity. You've measured delta G, you've measured delta H, you calculate SXS. This can't be right, but this is just precision of the data. That's positive. It certainly ain't going to be that. I'm going to do one more. Okay, number 3 was liquid solutions of lithium potassium chloride. For these liquid solutions, you have the heat of mixing, you have the excess entry mixing. Calculate the activity at 1000 Kelvin when the mole fraction of potassium is 0.25. All right. So I'm going to put this back on bigger again. So what did we have? We had delta H. Okay, it's an ideal solution. A regular solution. It's a regular solution whereby delta H of mixing is a constant times x1, x2. And so then this means that delta H of 1 is omega times x2 squared, and the delta H of 2 is omega times x1 squared. Right? We did that the other day. A regular solution, it's parabolic for the integral property, it's parabolic for each partial property. And similarly, SXS is eta times x1, x2, so SXS of 1 is equal to eta times x2 squared, and SXS of 2 is eta times x1 squared. Okay, so that minus 17.86 is omega and minus 1.46 is eta. Going backwards in this then, what we're trying to calculate is we're trying to calculate the activity of potassium chloride. And what I want, if I want the activity of potassium chloride, I want the delta G partial of KCl, also known as delta mu. KCl, the delta G of KCl is RT log activity. That's your definition of activity. So I need to calculate the activity of KCl, I need its partial molar Gibbs energy of mixing, or partial relative chemical potential of mixing. Okay, and the delta G of KCl is the ideal, delta G partial ideal. The ideal partial Gibbs energy is RT log X, and the GXS is delta H minus TSXS. So this is delta G of partial is delta G ideal, plus these two terms together are G excess. And G excess is delta H excess, or delta H partial minus TS excess partial. So your delta H partial is the same constant times X lithium chloride squared, and S excess is the constant times X lithium chloride. Okay, so there's your partial of KCl and your partial properties of KCl from these equations here on the board. Now you put them together with the ideal and you get the activity, and that's got your activity, so you can calculate it here. Okay, well, all the other ones are similar. Let's take a break and then finish those up.